Welcome to the fourth video of my model storage robot project. Today we're finally going to see the robot in action. This is the big picture I developed in the first video of this series. The second video covered the hardware design and build process, and in the third video I described the interface that will connect the robot to the Photon. Today I'll be focusing on the programming of the robo interface and its implementation of the command interface specified in the third video. We'll be relying on a lot of information from the previous videos, so if you haven't watched them yet, now would be a good time to pause and do so. This is the hardware you already know. We've got 4 axes to control: X, Y, Z, and the pinces, each one with an impulse counter and an end switch. Additionally, we've got an input sensor and a color sensor to take care of. All of these components have to be managed to implement the command specified earlier. This is the prototyping board I used to connect to the interface. On the top left side, you can see the ribbon cable coming in. It is connected to a standard 10-segment LED strip to visualize the state of the data lines. Since I'm notoriously bad at remembering which line is where, I've printed a small overlay. If you want to build something like this for yourself, be aware that there are 2 kinds of LED strips. Some do come with current limiting resistors built in and some don't. These didn't, so I had to add the small black resistor networks next to the LED strips to prevent them from burning out. You can ignore the other resistors down there for a moment. I'll talk about them in the next video. On the right hand side you can see the manual command input. Of the 8 microswitches, only the first 5 are used and connected to the command signals using the green cables. Note that the order is reversed through the cabling to have the LSB command 0 line on switch number 5 that is in the rightmost position to facilitate command entry. The ready signal is connected to the blue push button because it will only be set for short periods of time. The robo interface and the extension module attached to it are programmed using an environment called RoboPro, which is shown here in a video from a different project. Basically, you draw executable flow diagrams. You have a number of different diagram elements available, and you simply place them in the appropriate order and connect them with blue connectors to specify the control flow. Some elements also require data flow to be drawn using orange connectors. Like most other programming environments, RoboPro supports the use of subroutines to maintain a healthy program structure. So before we start to dive into the details, let's take a look at the overall structure. We'll be using multiple threads for this project. Although it's technically not required, I like to keep the thread start instructions in central location for a better overview. In this case, that's simply the main module that starts 3 separate threads, a controller and a tracker, to coordinate the movements, and a command loop that handles the external communication and command execution. The command loop uses a separate subroutine to read the incoming command. It then defers the actual command execution to a set of specialized subroutines, which in turn use a set of basic routines for common tasks. Let's take a look at these individual routines. This is the main module, kept very simple on purpose. You can see the 3 threads here: the command loop, the controller, and the tracker. When the robot is switched on and the robo interface has completed its internal checks, these 3 threads are started simultaneously. The first noticeable action is the initialization routine, so let's concentrate on that first. We have to remember that we know nothing about the state and position of the robot when it is switched on. It might be safely stowed in its home position, but there's no guarantee for that. It might have lost power while trying to store or retrieve some peas, its arm extended into the storage area. It might even have been powered off as an emergency measure because something bad has happened. We don't know. The job of this subroutine is to get the robot from its initial undefined state, or any state for that matter, into a stable home position. By the way, if you can't read the program element texts because of the video compression, check the GitHub repository linked in the description. It contains the original high-resolution screenshots. The first thing to do is to set some global variable named initialize to 0 and wait for 0.2 seconds. We'll see what that does in just a minute. Then it checks whether the switch I4 is closed. That's the end switch on the y-axis. So this is the check for, is the arm already fully retracted? If it isn't, then the corresponding motor is switched on and the program pauses until the switch I4 is set. Then the motor is switched off again and the two global variables are set. We know the actual Y position is 0. That's just an arbitrary definition, but it's handy to know that at the end switch is position 0 on all axes. We also set a nominal Y position to 0. Again, we'll see what this is about in a moment. It's important to start the initialization by fully retracting the arm first. This way, we know the pincers are in a safe plane where they can't collide with the storage structure or one of the sensors. Now we can continue and move the carriage to its rightmost position. Then we open the pincers, dropping anything the robot might be holding into the output slot F. There are a few extra steps here to deal with some mechanical quirks of the end switch. Finally, we'll calibrate the Z-axis by moving all the way up. For good measure, we also leave the output lines in a defined state and set the mysterious global variable initialized to 1. Let's take a look at this routine in action. Now, while it is possible to execute the programs from the development environment and watch the system stepping through the individual actions, that's not nearly as useful for real-world development as it might sound. For one thing, most of the steps happen very fast, so you wouldn't be able to follow the action anyway, which is why I won't show it in this video. It is possible to single step through the commands, but with motors pushing components against the end switches and desperately trying to tear them off, that's usually a bad idea. Also, executing a program from the PC produces a noticeably different timing behavior compared to programming the robo interface and letting it execute the compiled program on its own. Ironing out the issues caused by these timing differences can be very time-consuming, so I try to avoid using the online mode if possible. Anyway, here is the robot in some unknown intermediate state. We can see that it has apparently just picked up some part or was in the process of storing it when it was switched off. We can see that, but the robo interface can't, so let's turn it on and see how the initialization routine deals with the situation. As you can see, the robot is now in a clearly defined home position, ready to commence its first task. In order to understand how that works, we'll examine the 3 threads that do the actual work. We'll start with the controller thread. It basically consists of 3 blocks for the axes X, Y, and Z that are identical except for the variable names, switch, and motor assignments. You can also see that this is an endless loop. After the Z block is completed, it starts again at the beginning. Before any of the blocks are processed, there's a weird little contraption in the control flow. The system checks whether the global variable initialized is set to a value greater than 0. If it isn't, if the robot is not initialized, then it will enter a shortcut right to the beginning. Now remember the beginning and end of the init routine? That's where we set that variable to 0 before doing any of the initialization work and set it to 1 once we were finished. The reason for this is simply that the controller routine we see here is responsible for the motor control, and we don't want it to switch any of the motors on or off and interfere with the initialization. The global variable initialized is simply a kill switch that turns off the controller until the robot is in a defined state. Now what does each of these blocks do? For each of the 3 axes controlled here, there are global variables that hold the current position and the desired target position. The first step is to compare these values. If the actual position is lower than the nominal position, we'll set a direction variable to 1, we'll see later what that is for, and turn the motor on in one direction. If the actual position is equal to the nominal position, we set the direction to 0 and stop the motor, and if it is greater, we set the direction to -1 and turn on the motor in the opposite direction. Now that direction turns the part of the robot towards the end switch, and if by some accident we hit the end switch, we immediately turn off the motor. Since we now know where we are, we set the actual position to 0. This process is repeated for each of the 3 axes responsible for movement. The pincers are controlled differently because they need some special procedures. The second process that is responsible for the low-level control is the position tracker thread. It consists of 4 blocks, 1 for each axis, that are also processed in an endless loop. Each block compares the state of the impulse counter switch to a local variable. I don't know if you'll be able to see the orange L after YouTube's compression algorithm has had its way with the video. If the values are different, we add the value of the global variable direction to the global variable containing the actual position. You'll remember that the direction is either 1 while we're moving away from the end switch on that axis, or -1 if we're moving towards the end switch. This way, we count the number of impulses, or more precisely half cycles, we're away from the home position. Finally, we update the local state variable. Originally, I had the single thread that integrated both the controller and the tracker actions. That didn't turn out to work. The entire loop was relatively long, so the tracking state checks were executed at intervals so long that they started to miss impulses. That led to irreproducible results, which were quite hard to get rid of. I guess the lesson learned is, make sure that whatever is keeping track of the current position can do so without being interrupted. Now onto the third thread, the command loop. Again, this is an endless loop that first calls a subroutine and stores its result in a local variable. Let's take a look at that subroutine first. This subroutine implements most of the communication protocol developed in the previous video, so let's walk through this. After a brief delay, we ensure that the busy line is active, and since that is an inverted line, this actually means that the robot is not busy and waiting for a command. We then wait until the ready signal is pulled up by whoever is talking to us. When that has happened, we calculate the command code from the CMD lines using some simple arithmetic and deliver it to the output value of this routine. Then we pull up the acknowledge line to signal that we have picked up the command and wait for the ready signal to be dropped again. When that has happened, we lower the busy and acknowledge signals and get to work. Let's take a look at this communication process as it's happening. Here we have the robot fully initialized. The busy signal is active, so it's waiting for a command. Let's tell it to move to position E1, that's 10001. You can see the corresponding command lines lighting up. Now we'll give the ready signal. You can see that after a very brief delay, the acknowledge line went up, so the robot has accepted the command and is waiting for us to release the ready signal. We'll do that, and the robot gets to work. Once it has completed the movement, the busy signal goes back up again. Once again in slow motion, we'll move on to position D1, that's 01101, and now ready goes up, acknowledge goes up, ready goes down, acknowledge and busy both go down, robot completes the move, and busy goes up again. Most of the blinking lights you see here are controlled by the read input subroutine we just discussed. The result of that routine, the command code, is fed into what in any other programming language would have been a case or a switch case statement. In RoboPro, we don't have that operator, so we'll just have to use a cascade of comparison operators to branch to the corresponding subroutines. Note that the navigate and drop command implementations receive the command code as a parameter because they need to compute the location to navigate to or drop to from the command code. Before we can investigate the individual command implementations, we need to take a look at these three basic routines that are used throughout the implementations. The first one is really simple. It just compares each actual position value to its nominal counterpart, combines the results by using an AND operator, and waits until that turns true. This routine simply blocks until the desired target position is reached, which is often needed to synchronize stuff and keep the movements coordinated. The second routine opens the pincers. This is relatively straightforward. Check if the end switch is closed, that is, if the pincers are already open. If they aren't, set the direction to -1 and turn the motor on. Then wait for the end switch to close and turn the motor off. Then set the actual position to 0 and reset the direction value, and we're done. Closing the pincers is a bit more involved because we want to sense whether we have actually gripped anything. We do this by keeping track of the current position using a local variable named lastP for last position, then setting the direction, turning on the motor, and waiting for a third of a second. We then compare the actual position, that will have been updated by the tracker thread in the meantime if the pincers have moved, to the last position we stored earlier. If the value has changed, the pincers have moved and probably are still moving, so we'll just continue moving. If on the other hand the value has not changed, then the pincers have stopped moving, so we turn off the motor. We then check the actual position as determined by the impulse counter. If the pincers have closed to a position of 12 clicks or more, then they have moved too far to have picked up a piece. In this case, we open the pincers again to return to a defined state. Finally, all of the commands that require the pincers to close are supposed to signal whether the robot has picked up something, so we'll set the output lines accordingly. With these routines in place, we can now move on to the command implementations. The first one is the navigate command, and doesn't that look nice? Schadenfreude would be the appropriate German word, but let's see what it does. You'll remember that we get the position embedded in the command code and we have to decode that. The codes range from 1 to 20 and are grouped by column, so the column is simply the result of the integer division of a command -1 divided by 4, and for historic reasons we use a 1-based counter here. Column A is number 1, so we add an offset of 1. For the row number you might expect a modulo operator, and you can even draw one, but for some unspecified reason the RoboPro software refuses to compile the program for the Robo interface if it contains a modulo operator. Needless to say, it does so without any explanation or meaningful message. It doesn't even tell you which one is the offending operator. So we need a workaround that fortunately isn't too bad to read or implement. If you turn these formula into a flow diagram, this is what you get. Please remember that when you next encounter a solver for multi-line differential equations, things could always be worse. Now that this contraption has calculated the target coordinates for us, we first need to ensure that it's safe to move the arm around. That shouldn't ever be necessary, but just in case we wait until the arm is retracted. Then we look up the absolute x and z positions from a list of values each. These values were determined experimentally. They are then transferred to the nominal variables, causing the controller thread to kick in and move the robot around. In this routine, we simply wait until that's done. Let's see how this looks in action. Due to the design of the controller and tracker threads, the robot can either move horizontally, in this case to A1, or it can move vertically, as in this case to A3, or it can move diagonally back to E1. Now that we can move around, let's handle some cargo. First, let's see how we can pick up a piece from the input area. Again, we'll first ensure that the arm is retracted, then navigate to the coordinates of the input area. Note that this specifies a vertical position slightly above the board. Now, we'll make sure that the pincers are in open position and then extend the arm so that the pincers surround any piece that might be lying there. Only then we'll lower the arm to the actual board level and close the pincers. The reason for this extend, lower, grab movement pattern is easy to explain once you've encountered the problem it solves. With the parts used here, the robot always has a certain tolerance when it comes to positioning. If you position the pincers at what you believe to be the exact board height, you might end up half a millimeter too high, which would be inconsequential, or too low. If the pincers are too low when the arm is extended, they'll collide with the edge of the board. The robot doesn't know that, of course, and keeps extending the arm, thus forcing its carriage off its tracks. Believe me, that's something you don't want to see happen too often. When the pincers have closed, we'll pick up the piece and retract the arm again. We now might be holding on to something, and then maybe again, maybe not. The input might have been empty after all. Again, let's look at this happening on the model. For the first try, let's simply ignore that there's nothing there to pick up. We'll issue the pickup command, that's 10101, and the robot moves over and starts to extend its arm. Now it closes the pincers and finds there's nothing there, so it opens the pincers again before retracting the arm. Note that the cull lines are turned off to show that nothing was picked up. Now let's try this again with the piece in place. We still have the command encoded, so we can simply issue it again. Notice how the pincer motor is stopped once the pincers are no longer moving. Now that the robot knows it has picked up a piece, it turns on the call lines. So what do we do next? Well, we could store the piece somewhere. We already know how to navigate there, and from the pickup command implementation, we know that we need to position the arm slightly above the bin floor before extending it. In fact, the Z coordinates specified in the navigate command are all designed to be 9 clicks above the board level, so before moving around, we take the current position and add 9 to it, because the Z-axis counts from the top down, so greater numbers are further down, and then extend the arm. Then we lower the arm, open the pincers, and retract the arm again. The store command implementation looks very similar. Calculate the target Z position, ensure that the pincers are open, you wouldn't want to ram a second piece into an occupied bin, then extend the arm, lower the pincers because dropping the piece might cause it to float around and land off center, open the pincers, and move out again. How does this look when applied to the model? Here we have the robot with the piece we just picked up. Let's move this to an empty bin, let's say D2, and then store it. Now move over to another bin, for example C3, and then retrieve its contents. So that works, but wait. We've just stored a piece we won't know the color of. Or rather, we know because we can see it, but the robot doesn't. Well, we've got a color sensor, so let's put it to work. Again, we'll first ensure that the arm can move freely. Then we'll move to a target position, extend the arm, and lower the piece to its target position. Now we'll turn on the light above the piece and wait for a moment for the analog-digital converter to pick up the changed input value. We'll store that value in a temporary local variable, wait for 0.2 seconds, and read a second time. Then we'll turn off the light and move the piece back out again. From the two readings, we calculate an average value and evaluate that. From the second video, you'll remember that the color sensor will produce characteristic values for each of the colors. We'll have to turn that into 2-bit values for each color, and again, that's done with a chain of comparison operators. If the value is greater than 975, it has to be a black piece whose binary code is 11, so both lamps are turned on. If the value is less than that, but still above 750, we're seeing the green background, so no piece is present, that's result 00. If the value is between 600 and 750, it's got to be a red piece, 10, and anything below that is a white piece, 01. So back to square one, we've got a piece picked up, let's check the input. The piece is moved into the sensor. Then the light is turned on and the readings are taken. Now the piece is moved out again. And you can see the result. Col 0 is off and col 1 is on. That's 10, so it's a red piece. Now if we want to get rid of, deliver pieces, we again need to navigate around first. This implementation resembles the navigate command, but in this case the arithmetics are a bit easier. We calculate the columns, look up the X position, and move the carriage there. We don't need to move in the Z direction, which is good because that's a relatively slow axis. Then we open the pincers and let gravity do the rest, like this. Here we've got a piece, let's drop it into slot B. There you go. Now there's only one command missing and we don't even need to move anything for that. To check the input area, we simply turn on the light of the photoelectric sensor, wait for a moment, and then set the output lines depending on the input signal from the phototransistor. Now, don't forget to turn off that light again. Seeing this is a bit less exciting than the other commands. We issue the command, and the light simply flashes. Both col lines are off because there was no piece in there. Let's change that and try again. There you are. Now there's something to be picked up. Now let's use these building blocks to actually do something. Let's assume that this is the current state of the bins. We'll check the input, and in case there's a piece in there, we'll pick it up, check its color, and then store it. Then we've got an order to fulfill. We need to deliver 2 red pieces to slot B. Just for demonstration purposes, we'll then recalibrate the robot and fulfill the second order to deliver 2 white and 1 black piece to slot D. For reference, here's the command list, and this is what we'll need to tell the robot to do its job. Robot assembly kinda. Note that the robo interface does not keep track of the contents of the storage bins, which is intentional since it doesn't have a persistent storage that would survive a power loss, so we'll have to determine which pieces to take from where and where to store what manually at the moment. So let's go ahead and do this. So before we can do anything else, we have to switch the robot on. After it has completed initializing itself, let's check whether there's something in the input. That's 1, 1, 1, 1, 1, and execute. As you can see, there's nothing in the input. You can check again. Still nothing. So let's place a piece there. Try again. And now you can see the LEDs have lit up. So the robot has sensed there's something there. Let's try to pick up that piece. Pick up is 10101. So we have to reset these. One, 0, 1, 0, 1, and execute. That didn't work so well. Due to many mechanical tolerances, I have to place the piece a little bit further forward. That's more like it. Now we can see that this is the red piece. The robot doesn't, so we have to check the color. Checking the color is 11000 and execute. Now you can see 1, 0, that's red. We know now it's a red piece. Let's store that red piece in bin C2. So we have to navigate there. That's 0, 1, 0, 1, 0. And then store, that's 1, 0, 1, 1, 0. Now in the meantime an order has come in, so we need to deliver 2 red pieces to slot B. So let's take the red piece that's in C3 to navigate there. That's 01011. And retrieve, that's 10111. And to drop that into slot B, that's 11010. That's the first red piece, and as a second red piece, let's take the one we stored earlier in C2. C2 is 01010. And retrieve again is 10111. And drop to B again is 11010. Now in the meantime something might have come up, we don't know. Let's just, for good measure, reinitialize and recalibrate the robot. It's all zeros. And in the meantime another order has come up. We need to deliver 2 white pieces and 1 black piece to slot D. So let's navigate to D1 first, that's a white piece. D1 is 01101. And retrieve, that's 10111. And drop to D, that's 11100, which in this case is relatively fast. Now the next piece we pick up is from D3, that's 01111. And retrieve again is 10111. So obviously that's the black piece. Drop this to D, that's 11100. And finally we need another white piece. We'll take the one from E3, that's 10011. And retrieve. And drop to D. And that's about it. If you're interested in the progress of this project, there are a couple of ways to keep up to date. I have created a YouTube playlist you may want to follow, but of course you're also welcome to follow my entire YouTube channel. I'll also be blogging about this on the SAP Community Network, SCN, the link is in the description. You'll find the articles in my personal blog as well. If you're interested in the source code, check my GitHub repository. If you have any questions, suggestions, or would like to leave any other kind of comment, feel free to use any of these channels to get in touch. I'm looking forward to it. Thank you for watching and have a nice day.